So there's a question here that I'm suspecting a lot of people will have issue with. So I may as well just do it here for all of us. So it's page 177, question 7. Okay. So we have an integral. So let's write it down. So the integral from 2 to 4, 1 over 2x squared minus 12x plus 36. 26 dx. Okay, so the first thing we would say here is that, is it in the tables? No, it's too complicated. The second thing would be, is there a manipulation? Now, you've got a toolkit of manipulations, and one of them, obviously of interest in this chapter, is complete the square. So we're looking at complete the square. When it's complete the square, maybe we should just look at the antiderivative without worrying about the limits initially. Actually, no, there's probably no need for that, actually. Now, you have an issue. So we're going to do manipulation. We're going to deal with 1 over 2x squared minus 12x plus 26. And the naive thing that you would have been taught by me to do is that it's a plus x squared. So you should complete the square. You should try and write this as a squared plus x plus b squared. Now, the problem with that is, and we'll see, it's just not going to work. So let's see what happens. So you get a squared, and you multiply out the right hand side, you get x squared plus 2bx plus b squared, and you're left trying to compare 2x squared minus 12x plus 26 with x squared plus 2bx plus a squared plus b squared. Okay, so the first thing, and I always try and get you to do this, is to check, do the x squareds match? And the answer is here, they do not. So this has failed. Now I'm going to show you 3 different ways of dealing with this, and we'll carry out all 3. So the first thing to do is to say, okay, I have, and I think it's actually equivalent to the second thing I was going to do anyway. Not exactly. Okay, so the first way would work something like this. You've got 2x squared minus 12x plus 26. Now you want an x squared, but there's a 2x squared. So what you could do is you could take out a common factor of 2. And so you'll have 2 times x squared minus 6x, because 2 by minus 6 gives you minus 12, plus 13. Okay? And then what you can do is, instead of completing the square with the 2x squared minus 12x plus 26, you can do it instead for x squared minus 6x plus 13. We can set this to be equal to, and we'll use the formula we just wrote, x squared plus 2bx plus a squared plus b squared. I think I'm not going to bother actually calculating the integral. I'm just going to do the antiderivative. So now we have that the x squareds match, which is good. Now what about the b's, or should I say the x's? So I got minus 6 here and 2b here. I want those equal. And the constants, I've got 13 and a squared plus b squared. So first of all, we'll do the 2b is equal to minus 6. Divide both sides by 2. I get b is equal to minus 3. And now I'm looking at a squared plus b squared is equal to 13. I know that b is minus 3, and b squared therefore is minus 3 by minus 3, which is plus 9. And then we can take away 9 from both sides to get a squared is equal to 4. And then we can take the square root of both sides. A is equal to plus or minus the square root of 4, but we can just take the positive one. We can just say we only need one of them. So what do we have? We have 1 over 2 x squared. Should we go back? 2x squared minus 12x plus 26 dx. We took out a common factor of 2 from the bottom. And you see that 2 there is divided by 2, which is the same as a half. And so now I wouldn't write this next line, but I'll just to show you exactly what's happening. So this is the same as this. Okay, and then a constant multiplying can be taken out as a constant. So I wouldn't include this line if I was doing it myself. This, what I'm doing now, could be done before I completed the square, but I've already completed the square. A equal to 2, b equal to minus 3, so I have a half antiderivative. Actually, I will finish it off just to deal with the half. So a squared is 2 squared plus x plus b, x minus 3 squared dx. Okay, so let's go back and look at our integral. So if I go back and call this thing I can say that I is equal to the integral, well, I'm fixing the half, aren't I? Half integral from 2 to 4, 1 over 2 squared plus x minus 3 squared. I'm going to do a little substitution here. W is equal to x minus 3. dw dx is equal to 1. And multiply both sides by dx, I get dw is equal to dx. Now when you go from x to w, you really shouldn't use the same limits. You can change limits, but I think it's better to suppress them, so just forget about them for a line or two. So now this is in the table, so we can anti-differentiate. So fix the half. 1 over a inverse tan w over a. And now you can put back in the limits, a half, so you can multiply them together and get a quarter if you want. Inverse tan, and w is x minus 3 over 2, 2 to 4. So now we do top limit minus bottom limit. So I'll fix the half, or I could multiply it in, doesn't matter. Half inverse tan, so 4 minus 3 over 2, minus a half inverse tan, substitute 2 minus 3 over 2. I'm just going to bang that into the calculator and get round what I have to 4 significant figures. So I'm going to probably do the quarter. Actually, I'm going to take out a quarter altogether. Then I have inverse tan of 1/2 minus inverse tan of minus 1/2. And I get 0.2318. I mentioned other possibilities, so there are 2. So the other possibility is when you get to, so if x was a 2x squared minus 12x plus 26, and you said you want to be this to equal a squared plus x plus b squared, and then you discovered it just couldn't work. So that's up here. So this with the exclamation mark, it's not an equals. It's you want them to be equal, and here it just didn't work. But I mean, you can do whatever you want on the right hand side. Oh, I want this to equal that, I want this to equal that. And so what I could do actually here is to fix it, I could multiply the right hand side by 2. Now you must say, oh, hang on, you multiplied one side by 2 and you didn't do anything to the other. But it wasn't an equation. So I only wanted them to be equal. And now what I have is, it might be possible to have these two things equal to each other. And indeed, if you follow it through, so you'll get 2 by, say, x squared plus 2bx plus a squared plus b squared. And then you get 2x squared. 2 by 2b is 4bx. And then the 2 by the other thing is, say, 2a squared plus 2b squared. And now you will want the x squareds to match up, and they do. You'll want the x's to match up, and notice you'll get b equal to I'm a bit confused now. Was it? Oh, you get b equal to minus 3. Oh, that's the same as last time, yeah. And then 26, you'll get the same thing as well. So that's the second option. The third option is a bit more nuclear. So the third option would be to say, okay, I have 2x squared minus 12x plus 26. And what you can do is you can introduce another constant. So you can keep your a squared, and then you multiply x by something as well, say cx plus b. Now this is one where it turns out that you really need to do the substitution. So let's just carry this out for argument's sake. Now look, let me be clear. I think the first way, just taking out the common factor of 2, is the way to go. The second way is somehow equivalent to that. The third way is harder than you need. But the only real reason I'm looking at this third way is in case somehow you end up there, and just showing how the W substitution is important. So we multiply this out, we get a squared plus c squared x squared plus 2cbx plus b squared. So you get c squared x squared plus 2cbx plus a squared plus b squared. Now everything's going to be a little bit harder, but I just want to show you about the substitution. So when it's like x plus something or x minus something with nothing else, so x plus or minus a constant, you really don't actually have to do the substitution. This is the one where you do. So let's compare. We want 2 to equal c squared. We want minus 12 to equal 2cbx. And I want 26 to equal a squared plus b squared. Let's go. So c squared is equal to 2. You do the square root of both sides. So you'll be the plus or minus the square root of 2, but we're just going to choose the square root of 2. Then we want 2bc to be equal to minus 12. We know that c is root 2. And we divide both sides by 2 root 2. We get b is equal to minus 12 over 2 root 2. And there's different things you can do here. I like to maybe multiply above and below by root 2 just to make it look a bit nicer. So I get minus 12 root 2 over 2 by, and root 2 by root 2 is 2. And then the minus 12 over 4 is minus 3. So I get minus 3 root 2, which is a bit nicer than what we had. And then finally a squared plus b squared, I want that to equal 26. So we know that, so I need to square minus 3 root 2. And if you do it, you'll get 18, I think. Because 3 by 3 is 9, root 2 by root 2 is 2, 9 by 2 is 18, equal to 26. Take away the 18 from both sides, a squared is equal to 8. And then a is equal to plus or minus square root of 8, which is plus or minus 2 root 2, and we'll just pick 2 root 2. So you end up with, therefore, 1 over, what was it, 2x squared minus 12x plus 26. Let's do this, complete the square, so it'll be a squared, and a was 2 root 2, plus cx, which is root 2x, minus 3 root 2 squared dx. So that's the new complete square. And now, because the multiple of x is not 1, the substitution becomes important. So you let w equal to root 2x minus 3 root 2. And now you don't get dw dx equal to 1 anymore. You get dw dx is equal to, fix the constant root 2, derivative of x is 1 minus 0. So we end up with dw is equal to root 2 dx, and then divide both sides by root 2, dx is equal to dw divided by root 2. So what do we get then? So this thing, which I'm going to call j, is equal to 1 over 2 root 2 squared plus, and then this becomes w squared, and dx is dw over root 2. And now let's do our, okay, the divided by root 2 is a constant that can be taken out. you'll definitely appreciate that what we did first was important. But if you went here and just did 1 over 2 root 2 inverse tan of root 2x minus 3 root 2, that would be wrong. Okay, we'll keep on going. We want to see maybe do we indeed get the same answer? Do we get this 1/4 inverse tan x minus 3 over 2? That's what we're looking for. So, well, we're ready to use the formula now. So I've got 1 over root 2. Now 1 over a here is 2 root 2, inverse tan w over a, which is 2 root 2. And now we said we want to get 1/4. If we go back, it'd be 1/4 inverse tan x minus 3 over 2. We seem quite far away from that at the moment, but look at the thing on the front. So that's two fractions multiplied together, top, bottom, bottom. So you get 1 by 1 is 1, and then root 2 by root 2 is 2, 2 by 2 is 4, so there's your quarter. Not there yet though. Let's see, inverse tan, what was w? Root 2x minus 3 root 2, all divided by 2 root 2, but what you can do inside in that thing is divide above and below by root 2. So root 2x divided by root 2 is x, minus 3 root 2 divided by root 2 is 3, and then 2 root 2 divided by root 2 is 2. So it does give you the same answer. Now obviously that was a completely bonkers way of going about it. I just really wanted you to show the importance of doing the substitution. If you just went from here to 1 over 2 root 2 inverse tan of this thing over 2 root 2, you would not have the right answer. Okay.